Let's start off with the definition of K connectivity. Definition. So a graph G is K connected if, I'll sort of put it in two ways, and be aware the definition of connectivity, there's a little bit of it that's somewhat technical, and so in different textbooks you'll see slightly different treatments occasionally, but this one will serve us well enough in this class. So a graph is K connected if it remains connected after removal of any set of K minus 1, so less than K vertices. Okay? So this like represents like how robust it is to removal and remaining connected. Originally, the definition of connectivity, when you just say a graph is connected, it means there's, for every two vertices, there's a path. It doesn't say anything about if you remove a vertex, whether it remains connected or not, okay? But ordinary connectivity is the same as being one connected. That's all we can claim, right? It remains connected after the removal of 0 vertices. That's what connected means, right? That it is connected in the first place. I mean, this definition relies on the original definition of being connected, okay? So if I tell you that it's connected, all that it implies to you is that it's one connected. It might be higher connected than one, but all it says, yeah, so let me like say, being connected implies one connected. Alternatively, so alternative, what we like to say is that in order to disconnect the graph, we need at least K vertices to disconnect it. You might need more, but you need at least K. So alternative, we need to remove at least K vertices to disconnect it. Okay. I'll give examples of these things in a moment, a few graphs, and we'll determine these values. But let me add one other thing. There's a special case, and that's the complete graph. So Kn. There's no way to disconnect a complete graph by removing vertices. Like, think about it for a little bit. Every time you pull off a vertex, you're left with a smaller complete graph that will always be connected at every point. You pull off a vertex, smaller complete graph. And so the only thing you do with the complete graph is remove all the vertices and make it disappear and become the empty graph. But that maybe is still connected. I don't know. Like, I mean, vacuously it is, right? Every pair of vertices has a path. There's no pair of vertices. So actually what we say for this one here is we will say that Kn is n minus 1 connected, which kind of makes sense. I mean, after the removal of n minus 1 vertices, you're still connected because you have a single vertex. We're going to say that the empty graph, once you've removed all the vertices, we're going to say it's not connected in a sense for the purposes of this thing. Generally, we don't talk about whether it's connected or not, but in for Kn, we just have this special case that it's n minus 1 connected. That's, in order to make it disconnected, we have to remove everything, is kind of what it's saying. Some people will write this definition in the following way, that it's K connected if, like, we need to remove at least K vertices to disconnect it or to make it empty. If you put it that way, then it would capture Kn as well. I just don't like that one because 99% of the time, you're not talking about the complete graph. And what's really important is removing K vertices breaks it into multiple pieces. But occasionally when we want to make theorems that hold for all graphs, it'll only work if we specify Kn to be n minus 1 connected as opposed to something else, okay? All right, so the maximum K such that G is K connected, right? A graph that's 1 connected, who needs at least 1 vertex removed to disconnect it, might be 2 connected. It might require actually 2 vertices to disconnect it, not 1. So if you're 1 connected, I mean, if you're 5 connected, you're also 4, 3, 2, and 1 connected at the same time. So typical question is, here's a graph. What's the biggest K for which it's K connected, okay? So the max value K such that G is K connected is the connectivity of G. That's the connectivity. So that's a parameter of the graph. And it's denoted, well, this is supposed to be kappa of G, but I can't draw a kappa that's distinct from a K. So K of G is the value of this graph. It's the largest value for which the graph is K connected. Okay. So I like to think of it, connectivity is one more than the largest number that is safe to remove from the graph. If you can remove 10 vertices and no matter how you always remain connected, then you're 11 connected. You're safe under the removal of one less vertex always. Okay, that's a bit of a sticking point. That's why in some ways this first definition is a little bit unsatisfactory, because K connected says safe under the removal of fewer vertices, not K, but fewer. But I don't love this definition here for that you need to remove at least K. But it's up to you, whichever one you prefer. Yeah. Okay. And actually, we will learn later. We'll find an important theorem that characterizes K connectivity in terms of a different property. And in a lot of ways, that'll be more useful. In fact, let me tell you what it is now, because it's good to have it in the back in your mind, but we won't get to it till next week. A graph is K connected if for any two vertices, you can find K different paths between them, right? And those paths, they can't like overlap in vertices, so there'll be K disjoint paths. And that's nice because that matches the original definition for connectivity. Connectivity says, is there a path? And 10 connectivity says, are there 10 paths, right? Are there 10 different wirings to get from A to B? And that's very sensible for like asking how connected like a network is. But this is the starting point definition. The other one, again, will be a characterization. And from then on, we can use it as a definition. Okay. So that's what's called vertex connectivity. There's also edge connectivity. Okay, so, and that's very similar. It's defined in the same way. It's just removing edges instead of removing vertices. And it has a little bit different behavior. So G is L edge connected if no set of L minus 1 edges disconnects it. Okay, I haven't exactly used this terminology before, but I hope it's clear. If I say, if a set of L minus 1 edges disconnects G, I mean that set of L minus 1 edges removal results in a disconnected graph. That's what it means to disconnect the graph. So it's L edge connected if it's safe under the removal of any L minus 1 edges. Same exactly situation as the vertex one. So in other words, must remove at least L edges to disconnect. Unfortunately here, the complete graph is not a special case here, right? The complete graph we weren't able to disconnect by removing vertices, but can someone tell me how we could disconnect a complete graph by removing edges?
Remove all of the edges on one vertex.
Perfect, thanks Andy. Yeah, if you remove all the edges on one vertex, that vertex is now separated from the rest of the graph, which actually happens to be a complete graph. But we had this advantage that the vertex didn't disappear, right? That's crucial. When you remove vertices, those vertices are removed as potential components in the resulting graph. But when you remove edges, all the vertices stick around, and so it's like easier to get components. Vertices don't vanish. And actually what Andy says there will be important in the first theorem that we'll prove, is that's always a good way to disconnect a graph, is just to remove all the edges incident to one vertex. Then that vertex is separated from the rest of the graph. That doesn't work in vertex connectivity in general. In vertex connectivity, maybe I can draw here, you might try to replicate that by saying, okay, well, if we remove these edges, it disconnects this vertex from the rest. Why don't we remove all these vertices, right? Maybe that'll disconnect it. But what's the issue here?
We still have a vertex that's connected.
Yeah, exactly. Connect in quotes is perfect, right? These vertices may literally be everything in the graph, and removing all of this just leaves this single vertex in the graph. And so that it's not adjacent to anything doesn't matter, because it's everything. It's maybe unlikely, but I mean, of course, it can happen. But with edges, you don't have this problem. So they have a different kind of behavior here. Okay. And then there's the edge connectivity. That's just the largest L for which you're L connected. So max L such that G is L edge connected is the edge connectivity of G. And it's denoted, at least a lambda I can draw, it's lambda of G. Okay. Other textbooks sometimes use kappa prime or other values like that. We're going to use lambda and kappa for these two. There's no reason why you can't talk about vertex connectivity. You can use the term vertex connectivity instead of just connectivity. But usually we just use the term connectivity for vertices and edge connectivity for edges. Vertex connectivity by far is the more studied and more, discussed of the two properties, but edge connectivity is relevant. Okay. So let me draw a couple figures here. These are in the notes, but just to sort of get a feel for how these parameters act here. Are those messages in the chat? Yeah, I didn't have it up. Let me pull it up here. Yeah. Okay, Andy Van, very good question. Our first examples will deal with this question exactly, and then you guys have a homework actually on this, so I won't answer it in its entirety. But let's look at this one, because the three parameters I want to discuss exactly are kappa, lambda, and little delta, which is the minimum degree. Right? These three are somehow related to each other. And so, what's kappa in this graph? Can someone tell me? By here, we're not proving anything. I mean, we're proving, but it's just by examination. Like, how can we disconnect this graph with the fewest number of vertices, right? That would tell us, by the way, the connectivity. The smallest set of vertices. Is it one? Yeah, it's one, exactly. The smallest set of vertices you can find to disconnect the graph, that's the connectivity. Because anything smaller would be safe, and therefore it would be one more than that smaller value connected. So yeah, so I mean that's another way to see it. So the connectivity, yeah, actually maybe highlight this real quick. This value here, the connectivity, this is the size of smallest disconnecting vertex set, right? That would be, according to sort of the alternate definition, the smallest set you can find that disconnects it, nothing smaller disconnects it. So this would be the smallest K for which it's, the largest K for which is K connected. Okay, so this, so it's kind of fun when that happens, but okay. So kappa's 1, right? We could, removing that vertex clearly disconnects the graph. This one doesn't work, but we can find one of size 1 that does. Lambda also 1, right? It's just absolutely right there in the middle. Clearly, if you remove that edge, you become disconnected. What's the minimum degree, though? 2. Yeah, there's a few vertices at degree 2. So we already see a gap between the edge connectivity and the minimum degree, but it's an upper bound still at the moment, right? Which is reasonable. All right, let's look at another example here. Give me a moment to draw this. I think I have 2 K4s here. One more vertex. Okay. What's kappa in this one? Pretty clear it's 1 as well. That central vertex is going to break it up into, you'll have a K4 here and a K4 here. The 4 edges incident to it do vanish, but you'll have two cliques. So kappa's 1. What about lambda?
2.
Does 2 work here? Yeah, I think 2 works here, right? If you delete this one and this one, you have everything that you had before on the left-hand side, but then you have this piece here, right? So 2 seems to be the minimum you can get away with there. Formally to prove such a thing, you need to show also that there's no single edge that disconnects it. I'm not going to go through all those details in order to do that here. It's just kind of by examination. In an actual proof, you have to come up with a trickier strategy to avoid checking every single edge. Fortunately, this graph's pretty symmetric, but lambda's 2. What's the minimum degree in this one? Let's see here. I think it's 3. Yeah, I think it's 3. Maybe I wrote in the notes 4, but it's 3. I think it's 3, right? Each of these complete graphs has degree 3 in them. And then, at least 3, right? They each have 3 from the fact that they're a complete graph. These 2 vertices have even more edges coming out. And then this central vertex has 4 as well. So minimum degree 3. So we see an example where all 3 of these values are different. Your first homework on this set will actually show that it's possible to make arbitrarily large gaps. You can come up with graphs that have as large gaps between each of these values as you like. So there's no easy way to relate them in general. And maybe one more example. Let's take a 6 cycle with the diagonals. There's no vertex in the middle. Yeah, good, I drew it that way there. And here we get kappa, lambda, delta. What's delta first, at least? That's 3, right? It's a degrees 2 around the cycle plus another edge going across. What about lambda? Again, here I'm not looking for a proof, so just trying to figure out the best you can come up with here. Is there any way to disconnect it by removing 2 edges? Seems very unlikely, right? Like 2 edges might disconnect the cycle, but you still got these cross edges that'll like save you. Could you disconnect it with 3 edge removals? Yeah, that's always safe, right? Just isolate a vertex by pulling off 3 incident edges. So 3. What about kappa? Here you can actually replicate the 3 removal. Like I could isolate this guy by removing this, this, and this. And then this would not be joined to this one or this one, like there wouldn't be a path. That proves that it's at most 3. Maybe there's a way to remove 2. There's not, but again, you have to check. So this one's 3 as well. So this was just an example to illustrate that they can all be equal to each other, right? So there's a lot of variety here. The kappa and gamma, or kappa and lambda, look like at first they seem like they're equal to each other or close to being equal to each other. Because by the way, in the complete graph, yeah, okay, so let me mention something here. So kappa of the complete graph n, this was basically just defined to be n minus 1, right? We said that the complete graph is n minus 1 connected. What about lambda of the complete graph? What's that?
Same.
That's got to be n minus 1 as well, right? We had but that one wasn't for like technical reasons. It was like it clearly followed the ordinary definition. What's the minimum degree of the complete graph? Also n minus 1. Every vertex has the same degree. So here's an instance where all 3 are equal to each other as well. Okay, so at least based on these things here, we have some information that might be reasonable to try and prove here. So in general, let's just let G be a graph. Then kappa is always, kappa of G is always bounded above by lambda of G, is always bounded above by little delta of G. So that much we know. They at least have that relationship there, but these gaps can be large, but you never have kappa greater than lambda, lambda greater than delta, things like that. Okay, one of these we basically have already proved, like Andy's observation proves one of the relationships immediately here, okay? Let me look at those. Is that the order in which I did it here? Okay, yeah, we'll get to that in just a second. Let me deal with the sort of trivial cases first here. So if G is disconnected or trivial, so trivial graph, I didn't define this term yet in the class. The trivial graph is the single vertex graph. The empty graph is the 0 vertex graph, okay? So 1 vertex graph. And again, we should always have, remember, multigraphs in the back of our mind here. Multigraphs do not come into this statement here. So this is important that this be a simple graph for now, for the proofs we're doing today. I mean, if nothing else, like trivial is not clear what it is in a multigraph. You could have loops and stuff. But yeah, like I said, I generally won't specify simple, but I just want to put it here now. Okay, so if G is disconnected or it's trivial, then kappa of G equals lambda of G. They're both clearly 0, right? They're already not connected. So they're not safe. They're safe under the removal of no vertices at all, right? Like you don't need to remove anything in order to disconnect them. Actually, let me think here for a second. So it's disconnected after, yeah, okay, actually, you know what? The original definition I gave you here for it's safe under the removal of k minus 1 vertices, does not really work well in this case, because safe under the removal of -1 vertices is totally nonsensical. So there you should use the alternate definition, which is that you need to remove at least 0 vertices to disconnect it. Well, it's already disconnected, okay? So again, most of the time, basically always, we don't bother wasting our time with discussing connectivity of disconnected graphs. Like, that's stupid, right? That's like, so we don't worry about the 0 case. However, this does technically not make any sense in the original definition I gave you. So anyhow, and 0 is certainly at most delta of G, the minimum degree. Minimum degree could be 0 if the graph's trivial or it's a bunch of isolated vertices, but certainly minimum degree is not smaller than 0. So great. It's confirmed in the case when G is disconnected or trivial. The whole purpose of this is so assume G is connected and has at least 2 vertices. Which, by the way, would have been a reasonable place to just start the statement of the theorem. Let G be a connected graph on at least 2 vertices, but well, you know, whatever. So, okay. All right, so yeah, okay. So as Andy pointed out, if we remove all edges incident to a vertex, we'll definitely disconnect the graph, right? So remove all edges incident to a vertex of degree, let's say specifically a vertex of minimum degree, of degree little delta of G, disconnects G. So that immediately tells us that lambda of G is bounded above by delta of G, right? The smallest number of edges we need to remove to disconnect it has no reason to be above the minimum degree, because I can always exhibit a set of minimum degree many edges that will disconnect the graph. So this smallest value here that disconnects is no bigger than that, okay? So now all we have to show is that kappa is at most lambda. That's the content of the proof there. Okay, so if G is, what do we want, complete? Yeah. If it's a complete graph Kn, then actually we already figured this one out a moment ago, then all 3 parameters are equal to each other, right? Then kappa equals lambda equals little delta. And so we're done in that case as well. Okay. Yeah, I mean, they're all equal and they're equal to n-1. So that case is dealt with as well. So we can also assume G is not complete. Okay. Oh yeah, we won't use that till the next case. Well, maybe we use it in the first case here. All right, now we need to distinguish 2 cases. The first case is that lambda of G equals 1. Okay, so we have to resolve this case here. So if lambda of G equals 1, then it means that there's an edge whose removal disconnects the graph, right? Now, what we do here will be a helpful strategy in the next case anyway. I'd like to show that removing a single vertex also disconnects the graph here. Now, ordinarily, I'd say, well, I mean, then this will work. If I remove that vertex, it will have the same effect as removing that edge, because it'll destroy that edge. Now, that was problematic earlier, because removing this vertex might mean that this is all that's left over, and we don't actually disconnect the graph. Why is that not an issue here, though? If this was my entire graph, then what? This is a complete graph. 2 vertices with a single edge is technically K2, the complete graph on 2 vertices with all possible edges. We already dealt with those. It's not complete. So what it means is there's additional vertices. So like there's either stuff over here, or there's stuff over here, or like both, right? Let's pretend for a moment it looks like this, like it's sort of somewhat more interesting of the 2 cases. Then remove this vertex. It will isolate this vertex from whatever, there's at least one other vertex in there. If it's the other way around, remove the other opposite end there, okay? So it's crucial that we're in the not complete case, otherwise that doesn't work. But most of the time, in order to replicate removing an edge, we can remove one or the other end vertex and we're safe, okay? Then remove a vertex on either side Okay, I'm not writing out exactly what I explained here. You can't just pick either side. You have to pick the appropriate side to disconnect. And so kappa of G is also 1. It's not 0 because the graph is connected. Otherwise, this would be 0, right? So case 1, when lambda is 1, kappa is also 1. And everything works out here. Obviously, delta, we already proved is at least lambda, so we don't have to address that there. But it also clearly follows, right? Once you drew the edge, your delta is at least 1 immediately. Okay, so now, in case 2, we're going to have that lambda of G equals L, and it's at least 2. I'm going to fix this in the notes. In the notes, I specified lambda of G to be K, which is kind of obnoxious and mixing things up. Usually K is associated with vertex connectivity, so I'll change it over to L here. Okay, all right, so let's call it x1, y1, x2, y2, and so on and so forth. XL, YL be a set of edges that disconnect G. Okay, so here's L edges that disconnect G, and this set L is minimal, right? I mean, lambda of G is equal to L, so the smallest size set of edges that disconnected, there's L, many of those. I can't disconnect it with fewer. All right. Excuse me, guys. Okay, so let's look at these, and I want to employ the strategy I used up here, and let's see if we can or can't. Okay, so let's look at these edges here. They look like this. Let's make an observation or two about them. Let's see here. So some of the edges could look as follows, right? I'm not saying that these x1 up to xl are distinct vertices, right? The set of edges that I need to remove to disconnect the graph, they might have like n vertices in common. For instance, when you remove all the vertices incident to a single vertex, they were all incident to each other on one side. So I don't know what these guys look like, but this is the x, I, y, i's, those guys as removals. So let's say on the left-hand side, these are the x's, and the right-hand side are the y's, just to make life easy. Actually, is that clear that we can draw it that way? Yeah, we can. I mean, we can relabel if we need to in order to get the picture to look like this, okay? So if x1 up to xl disconnect G, so if removing the xi's disconnects G, then what can I say about the ordinary connectivity? Then what's kappa of G related to lambda of G?
It must be less than or equal to that value, because we found like a removal that works.
Yes, exactly, right? There might be a smaller removal, but in terms of a bound, it's fine. We know that L is the minimum number of edges to disconnect the graph, and I just found L vertices that also disconnect the graph. So kappa of G, okay, maybe it's even like clearer to say that kappa of G is therefore less than or equal to L, because I literally found the L vertices that disconnected, and L is lambda of G, right? So if these vertices on the left-hand side disconnect the graph, then I'm done. And this would have been using the same strategy as the one above. Replicate the edge removals by removing the incident vertices there. By the way, yeah, okay, also keep in mind that the xi's, these may not all be distinct, right? Like we drew over here, where there's actually less vertices than edges. But that only just strengthens our conclusion here, okay? So we have to assume this doesn't happen, okay? So assume x1 up to xl does not disconnect G. So how could that happen? If removing these vertices doesn't disconnect the graph, then after I remove them, everything that's left over is still connected. So let me illustrate something here. What if I put a vertex over here that looks like this here? Is such a scenario possible? Remember, we're here. These xi's do not disconnect the graph. If I remove them, the graph is still connected. Is this picture still connected after I remove the xi's? I mean, it must be, but the drawing won't be, right? Because this vertex will be left by itself here. So these xi's, they can't like send anything else out here. Otherwise, the graph after their removal would be disconnected. Right? Let me try to illustrate that a little bit better. Right? If they disconnect G, we're done. So their removal doesn't disconnect G. So these vertices, after I remove them, like this stuff here is all connected. So this is all connected, which is fine. I mean, these edges got removed, but like it's connected in here in some fashion, right? But the point is there's nothing over here, right? So these edges get removed doesn't mean the graph became disconnected, because these vertices also got removed. It's the same trick as looking at complete graphs. Remember, moving vertices from complete graphs doesn't necessarily disconnect it, because those vertices got removed as well. So it means when I remove these edges, these vertices were part of like the fact that it was disconnected. They got separated from other stuff. And when I alternatively remove these vertices and I don't disconnect the graph, because we know how to deal with that, that means that what's left over is connected. It means that there's like nothing crosses this bridge. There's nothing over here, because if there were, these vertices would be separated off from this set here. So what that means is, I can probably just undo that. It means that the xi's neighbors live where? Like one xi here, where can it have neighbors? It can have it among the other xi's. So, which implies an xi only has neighbors among the other xi's, and yeah, exactly, all the yi's and all the xi's among the other xi's and y. Okay. Yeah, there's a problem here. We need to figure this out. And the vertex yi. So I want to claim something stronger. So Max, what you said is absolutely correct. It's not enough to give us our theorem here. What I want to claim is, like, say we're looking at x2 here. x2 could be adjacent to these guys here. There's like no reason why it can't be adjacent to those, because they all vanish. And so, but I also want to argue that actually this picture here, where this x was adjacent to multiple ones here, is not possible. Okay, and that this was only possible to go here. And I'm not seeing it right now. Why don't you guys think about it for a second here? I'm gonna check something. I'm a little confused now.
Can you reiterate what the problem was?
Yes. Okay. So the issue is, okay, what I'd like to do. So let me tell you how the rest of the proof goes, because then there's just one step here. What I'd like to show is that one of these vertices' degree is at most L. If its degree, wait, hold on. Yes. I'd like to prove one of these vertices' degree is at most L. Then I can remove its neighbors to disconnect the graph, because there'll still be something left over, I claim, okay? So my goal is to prove that one of these vertex, actually any of them, has degree at most L. All right, I'll get to the next step. In order to do that, I'd like to say that its only neighbors are among the xi's, and like say we're looking at x2 specifically, I want to show it's just the xi's and y2. Those are the only things x2 can be adjacent to. That's what I'd like to prove, because that's L things, at most L things. As of now, I can't prove that. As of now, I know, as Max points out, that it's only adjacent to the xi's and possibly all of the yi's. That's more than L things. That's 2L minus 1 things, which is more than I want. So I'd like to rule out these other vertices in here. I want to rule out that it's adjacent to these guys here. And it's not, I'm not seeing it at the moment the way that I put things together. I haven't said anything that implies that. In a sense, what I'd like to rule out is this configuration here that I drew, imagining that it was possible. This shouldn't be possible in the first place. So let me think for a moment here. Let me actually look at something. And if not, we'll move on. But oops. Okay, I stopped sharing, I guess. That's not what I meant to do. Yeah, so why is this happening? What? Okay. Let me write down what we want. So want to show. Yeah, so Jose says because the xi, yi's, yeah, so Jose, that's true that those disconnect the graph. And I think the other fact that we have at our disposal here is that that set of edges is minimal as well, right? We know that there's no subset of them disconnects the graph. I think that's the information we need to use. I'm not seeing it here. So the reason I'm not seeing it is because these two edges here, them both existing, doesn't seem to cause us problems in that fact, because like removing this edge may still mean that I need to remove this edge here, right? I don't see why, because like this stuff can be connected over here, and in order to separate these vertices off from the rest of the graph, I've got to remove all the edges across, which could be as many as like L squared. You could have one edge across for each of these things. Oh, wait. I see, Van. So, yeah, I mean, so that's a pretty good idea, and that almost certainly works. It's just it's a little more than we need here. Maybe we have to be more careful with our numbers, because let me point something out here, and this actually probably solves it, which is close to what you're saying here. So what I'd like to show, okay, we know that the neighbors are among the xi's and the yi's. Now, the number of xi's that are here is actually reduced each time you have this configuration, right? So there's not actually, like in this picture here, there's not actually going to be as many xi's as yi's because of this. I put this thing here, it basically reduces it by 1. And so the number of candidates for x2's neighbors like decreases in xi as I have xj's that send more across here, okay? I don't know if this comes out to L. I think it should. It's just not, I haven't set it up carefully enough here for that to work. Although maybe if we pretend for a moment these vertices are distinct. So we can think about this for a minute here. I have another theorem I want to prove that there's no possible way I can prove, so we're going to end with this anyway. So maybe let's give ourselves a couple minutes to try and resolve this, and then we can wrap it up here. So let's look at. Okay, so first let's look at the idealized situation. The ideal situation would be that we have these edges and they're all distinct from each other like this. They're just disjoint edges. They don't share any end vertices. Here's the xi's, and the other side has the yi's. And I know that removing the xi's doesn't disconnect my graph, right? Because we already know that finishes the proof. So that means there's no vertices over here. You know, just think of this as a left to right picture. Now, each xi, say x1, is adjacent only to this guy across here. It can't be adjacent to anything else anywhere in the universe, otherwise that part will be disconnected when I remove the xi's. X1 could be adjacent to the other vertices in the set here. But now, the degree of x1 is therefore at most L, because it's got L minus 1 neighbors in xi plus 1 neighbor there. Then, in this case, now remove neighbors of x1. That doesn't always work, right? We know that removing the neighbors like might not disconnect the graph, but in this case it does, because removing the neighbors would remove all the vertices in xi plus this one vertex in yi, and then xi and say this vertex would not be adjacent, have a path between them because xi had no edges leaving it. So that would disconnect, okay? So removing neighbors of xi disconnects, and then kappa would be at most lambda, and that'd be the end of the proof. That's the idealized situation. When these edges that disconnected the graph were, they were non-incident. I can't claim that, okay? I can't claim that, and I won't claim that because the proof can't possibly work that way. But let's now modify it a little bit to figure out how we might recover things here. So now let's just look at like the first maybe troublesome scenario that looks something like this. Okay, actually this is a good exercise. We're kind of figuring out how you might prove a fact of this thing by fiddling about. Okay, so now I have in the Y set, I have L things, and in the X set, how many things do I have in this case here? Yeah, L minus 1 in this specific instance. Okay, this again, this is only one of infinitely many scenarios that we can have, but this is one here. Now this, same deal. Removing the X's doesn't disconnect. So say this vertex in particular, it's adjacent to this one, and potentially these other xi, the other xi's, nothing else. But here, what's the degree of x1 here? It's got 1, 2, plus how many vertices are here? There's L minus 3 of these, right? Sorry, L minus 2. Sorry, yeah, L minus 2 of these. Not that one, and there's L minus 1 in total. So the degree of here is still at most L, and the same argument as above works, right? So I think we're going to be fine no matter what, because why can't I move this? Yeah, I think the proof will work just fine then. So we've got the yi vertices. It's still a problem. Anybody see the problem? It's still a problem. The yi's might not be distinct at the same time as the xi's might not be distinct, right? We might have this scenario here. Something like that. And then this would say, here's 4 edges on 2 vertices per side. So that's still not resolved. But I think if the yi's are distinct, and maybe we can still argue from there. My tablet thing's not working at all. Forget this for a second. So if the yi's are distinct, I think we're okay. And maybe that's not even a problem. Let's do it this way. Let's say x1 is like the highest degree vertex among the xi's. And when I mean highest degree, I mean highest degree going to the yi's. It's the one that has the most number of incident edges of this removed set. Okay, these are the edges that L edges. That's the one thing we know for sure. There's L edges going across here. We don't know how, but there's L edges at most. Say x1, it has T edges coming out here. Then the number of other xi's here is at most L minus 1 minus T. Right? Because down here, there's L minus T other edges, and those expose at most L minus 1 minus T other vertices here. Okay? Then it's just an analog of this picture here, right? When L1 had 2 neighbors here, there were 2. I reduced this set by 2. Or I mean, I reduced it by 1 more, right? It was 1 less for this vertex and 1 less for the extra edge here. So if I have T edges here, I reduce this set. Oh, sorry, should be like that, but it's L minus T. And then x1 can only be adjacent to these T things plus these things down here, of which there are L plus T of them. I'm not even worrying about the yi's whatsoever. So the degree of x1 is at most L. And then I can remove all the neighbors of of x1 and disconnect the graph in the same fashion, okay? I'm gonna stop there. I know this part probably wasn't clear, but we came awfully close to fixing the problem there. It's not as simple as what's written in the notes. I'll try and fix what's in there. But, this will happen occasionally. I hope it's not too common, but frankly, I don't consider these things a total loss because, this is what the homework looks like, right? You gotta, you don't just start with a proof. You have to try stuff. It's not easy. So